So, I hope that everybody had a good holiday. Thanks for coming back. I appreciate you being here. Kind of an exciting. I think I mentioned that I've been making a sauna this summer. For the first time in my life, I put some tile down in the bottom. We'll see how it works out. It's a long day. My back was hurting on yesterday. I guess when I finished yesterday, I was pretty sore all day, but starting to feel like a human again, not like a hobbled old man, right? I don't know, this may be a mistake, but I have plans of buying a used 12-string guitar tonight, or tomorrow. So we'll see how that works too. So hopefully it's good. We'll see. I'm a little apprehensive. This is funny. I told my brother a while ago bought a smoker. He spent some time in Texas. And when he came back, he was like, "Oh, I want to get like a nice, good smoker, right?" And he called me to ask if it was like a good idea. And because he called me first, I told him, "Well, that sort of means you want to buy it, right?" Because I don't know how your parents are. I know when I asked my dad, he'll give me the cons of the argument first, right? So you'll hear the downsides first. So if you're really unsure, then at first I was looking at a previous guitar, which is an Ovation guitar. It's kind of like my dad's guitar. It's rounded at the back. It's got this beautiful sound, but it was like $400. I didn't really want to spend that much. So I called my dad first and he was like, "No, don't get that one." But then I found another one for a more reasonable price. So I'm going to go check it out tomorrow and hopefully it's good. Okay? So I know you probably don't care, but this is what I'm thinking about this morning. Aside from thermodynamics, right? So I hope that everybody had a great weekend. Right? That you got a chance to see some fireworks or hang out with family, or even just relax, right? Because it's nice to be able to take some days and do that, right? It's good for the mental health, right? So we're coming up on the second exam, and we've done what we're going to do talking about open systems, but then this next topic that we're going to cover today on Rankine cycles will be the last topic for the exam. Now, the nice thing is we've seen this a little bit already. We just didn't sort of formally name it, right? But just to go back through what we do with open system processes. So first we have to define the control volume. Then we ask what's going on with the mass flow, right? So we do conservation of mass because mass can take energy with it, right? Then we say what happens to the energy. Right, so we do the first law. We probably get an expression for the heat transfer rate, Q dot, or the power, W dot. And then sometimes, anyway, we'll have to ask ourselves, is this process possible? Right, so we might want to do a second law analysis and try to see if that entropy generation rate is positive. My advice for doing exam problems, really anytime, I think it's a good idea, but particularly when you're under sort of the time pressure of an exam, is to focus your attention first on getting the symbolic solutions. Start with these base level equations, make your assumptions, and then get to some equation, right? So maybe your equation looks like sigma dot equals m dot times s out minus s in, right? Or w dot equals m dot times h in minus h out. Right? Because all that stuff is agnostic. It doesn't matter what the problem is asking you in terms of what the fluid is or what the component is. You can do that for any open system problem, right? So if the problem is going to throw you a loop, it might be in how do you fix the state, right? And we know that fixing states can take a lot of time. So I always think, what's the highest rate of marks per minute that I can get on a test, right? So I think getting the symbolic solution is a good way of demonstrating that you understand how to do the problem, right? And it tends to take much less time than when you start to fix the states, right? So that's my general advice, right? Conservation of mass. Hopefully this expression is becoming familiar to you if it's not familiar to you already. We know that dm by dt is equal to the sum of m dot in minus the sum of m dot out. Common assumptions, which is not the same as assumptions we make every single time, are that the system will be at steady state and often one inlet and one outlet. If this is the case, we get the answer that the mass flow rate in is equal to the mass flow rate out. Right? So then sometimes we've seen that there's only one mass flow rate in our problem. For open systems, the equation gets a little bit more complicated. I've written it out here as it would be for an imperial problem, because I remember anytime that kinetic or potential energy term sticks around, my spidey sense starts tingling, right? The hairs on the back of my neck start to stand up, because in those terms, I have to divide by GC if I'm dealing with imperial units just to get the right quantity, just to get energy per unit mass. Right now, if it's a metric problem, it's still going to give me an issue. I don't divide by GC, but it'll probably be in joules per kilogram instead of kilojoules per kilogram, so I got to check the units there. But it's doubly hard maybe in imperial, because even after I divide by GC, often I'll get something like foot-pounds per pound mass, whereas when I look H up in the textbook, it will be in BTU per pound mass. So I might have to do something like divide by 778 to convert those foot-pounds into BTUs. Again, there's a list of common assumptions here associated with these different terms. If it's steady state, which in this class it will be, basically, right? So we'll cancel this one out. Often our open system components, we assume are simple systems, meaning that they either consume or produce power, or they transfer heat. So typically we can cancel out one of these two things, although I might ask you a question on an exam that lets you demonstrate what to do if you have, say, a turbine that's got heat loss associated with it, right? One inlet and one outlet would mean we'd get rid of the summation signs, and usually we'll cancel out, kinetic and potential energy terms as well. When we deal with the second law, remember, whenever we do second law analyses, really what we're trying to do is figure out what's going on with this entropy generation rate. And sometimes, depending on how the question is worded, sometimes you don't even actually need a numerical answer here, because really, to figure out if something is possible, we only need to know if sigma dot is positive or negative. So as an example, you could, I think in the past, we've asked multiple choice questions where we ask if this thing is possible, and one of the answers is there's not enough information to figure out if it's possible or not. Now, that can be true sometimes, right? But sometimes you can figure out if this term is positive, even if, say, you don't have the magnitude of the heat transfer, right? But if I tell you that there's heat loss in the system, for example, then maybe that would let you figure out what the sign of sigma dot is without knowing the value of sigma dot. So it's good to kind of write down the equation, make your assumptions, get to that symbolic solution, and then see, okay, well, what are the terms, right? Even if I don't know the magnitudes of the terms, if they're both positive after I've isolated for sigma dot, well, then that means it's possible no matter what, right? So if I'm heating something up, for example, and I know that the specific entropy is increasing and I'm adding heat, then I know that that the system definitely has to be positive, right? But you can do that mathematically and just figure out the terms of the equation. So after you get all your symbolic solutions, you'll invariably be left in this situation where you are trying to solve for delta H or delta S, right? This is not unlike the first exam where we were ultimately trying to solve for delta U, right? So after we do the symbolic part of the problem, we have to ask ourselves, what's the fluid, right? And we basically have two different types of answers. One is it's something like water where we boil and condense the fluid, right? So that's water, but it's also, going to be something like refrigerants when we start dealing with refrigeration systems. So that could also be under the vapor dome, right? And then we have to figure out what the phase is. So what's the fluid is always kind of a two-part question. So I say, what's the fluid? Oh, it's water. Okay, I know that it's water. Is it a subcooled liquid, or is it a two-phase mixture, or is it a superheated vapor, right? So it's kind of a two-part question, right? And sometimes it'll be easy, like if they give you quality, then you can figure out pretty automatically it's got to be under the vapor dome. But if, for example, you know that it's at the end of an isentropic turbine, right? So isentropic means delta S doesn't change, so you know S at the outlet, and now you look at that outlet specific entropy and you figure out, oh, well, is that above or below SG for the given temperature or pressure at the outlet, right? And then you can figure out, oh, is it two-phase or is it superheated vapor? So sometimes it's obvious what the phase is. sometimes you might have to do a little digging to see if it's, what the phase is. And in that case, I would take the property, maybe it's specific entropy, like I just said, or maybe it's specific volume. And I would look at the two-phase tables and say, okay, maybe I know a temperature or a pressure, so then I can find HF and HG, or VF and VG, or SF and SG. And I say, is the value that I have in between those two numbers, right? And if it's above SG, then I know it's superheated vapor. And if it's below SF, then I know it's a subcooled liquid. So that's why I like to look in the middle first, because it'll tell me if it's not in the middle, then it'll tell me which side I'm at, right? So I think that might save you a little bit of time versus kind of maybe starting at superheated vapor and going all the way through. Now, the other option here for what's the fluid is that it's an ideal gas, right? So maybe it's air or nitrogen or carbon dioxide, and we can assume that it's an ideal gas, right? Then the second part of the question is it constant specific heat or variable specific heat, right? And we've talked about different strategies for fixing states for ideal gases, right? So if it's variable specific heat, that means I can't use any expression that has CP, CV, or K in it, right? So instead I have to use something like table A22 if I was talking about air, right? But if it's constant specific heat, then I never have to look on table A22. Instead, I'm using CP or CV or K, right? Now, so if we're trying to find delta H, right, if we're trying to figure out what's going on with the first law, right, then maybe we're looking in tables, right? So this is certainly going to be true for water, right? If it's a subcooled liquid, we can also use the assumption that delta H is equal to CP times delta T. Although for liquids, CP and CV are the same, so you could just have C there. This is one that people often will forget, this ideal pump, right? It's delta H is equal to the specific volume times the change in pressure. You won't have to on the test demonstrate that you understand how to derive that expression, which we did in class, but you will have to demonstrate that you understand when to use that expression. So if you have an ideal pump or an isentropic pump, right, then you can use this assumption, right? And this actually simplifies to just either one of the specific volumes, because we assume that V3 is equal to V4 here, times delta P. When you do that, make sure you check your units, because we ultimately always want to have something like delta H in terms of, if it's metric, kilojoules per kilogram, because that's the H's we're looking up in the table, or if it's imperial, in BTU per pound mass. Then finally, if it's an ideal gas, you can either say delta H is equal to CP times delta T, that's if it's constant specific heat, or it's not listed on this table, but then you can also look up individual values of H on table A22. So if you know the temperature of the gas, which you would need actually for this expression anyway, you can go to table A22 and say, oh, air at 300 degrees Kelvin, that's going to have a specific enthalpy of some value. Delta S, we started to talk about this. There's one more thing that I'll say about this on today, right? So for solids and liquids, it's basic, or for liquids, things like water, it's basically the same thing. We're going to look on the same tables and look up the same values. But then we also have this new idea of isentropic pumps or turbines, right? We'll talk about compressors more later, right? But pumps and turbines and isentropic or ideal compressors will be the same, that the change in S across that device is going to be equal to 0, right? That's isentropic, right? And we can get that from the first or from the second law, provided that our system we can show is at steady state, is adiabatic, one inlet and one outlet, and ideal. And then we end up with delta S is equal to 0, right? So we talked about how for subcooled liquids, we can find delta S instead of CP times delta T. When we're finding delta S, we replace that delta T with the natural log of T2 over T1. For ideal gases, it's a little bit trickier, right? If we're doing variable specific heat, right, then we have delta S. On table A22, it's only got this S superscript 0 value. So this delta S superscript 0 is kind of like, oh, it's the change in the specific entropy related to the temperature change. But then we still have to account for the pressure. Right? You don't have to memorize that expression or any of these equations. They're on the equation sheet. And actually, because it's open book, you can make your own equation sheet too. I think that's not a bad way to study, is constructing your own equation sheet. We have also different expressions for when it's constant specific heat, right? Because these have CP in them. They look similar, right? The difference is, for open systems, we usually know the pressure difference. So you'll usually use equation B for open systems. But for closed systems, you know, when we're talking about pistons moving up and down, we'll often know the different volumes. So then you'll probably look at a ratio of specific volumes for closed systems. As always with ideal gases, when you use variable specific heat, your answer is more accurate, right? When you use constant specific heat, you gain in convenience and suffer in accuracy. And, you know, that accuracy gets worse as your temperature difference gets bigger. So one thing we didn't talk about for ideal gases is, how do we find delta H for isentropic systems? So if we have an isentropic compressor, for example, or you can have gas turbines where we assume that the working fluid is something like air, you might want to find a delta H in a case where the system is ideal, right? So we can look at something like Cp times delta T, right? Now, how do we find delta T if delta S is equal to 0? Right, so if we're trying to find the change in the specific entropy, or the specific enthalpy, sorry, delta H, when the change in specific entropy, delta S, is equal to 0. So there's a couple of options. So if I'm doing constant specific heat, then I'm looking for an expression that has K in the exponent. Remember, K is Cp divided by Cv. Right? So anytime you're using this, you've assumed that the specific heat is constant. Right? For open systems, we'll normally know the pressure differences, so you'll use this expression. Right? And this is all in the equation sheet, and I tried to organize it in a way that I thought was useful. So there is a part of the equation sheet that I think talks about, you know, isentropic ideal gas processes or something like that. Right? And then you know that you can use this expression. If you're looking for a system where you know the ratio of specific volumes, right? So a closed system usually, then you'll use this expression, which again has K in the exponent. It looks very similar. There is also this equation which relates the ratio of pressures to the ratio of specific volumes. I don't think in the, whatever it is, 6 or 7 years I've been teaching this class, that I've ever used that equation. But the first two are really useful. These equations, essentially, you won't have to derive them, but they fall out of our equations that we're using for delta S when we're using constant specific heat. So, so then we can use these expressions. There's another way to do this for variable specific heat, but I don't think I'll test you on that in the exam because we haven't really had a chance to talk about it. And it involves sort of looking at a new parameter on the table. So we'll do that when we start to talk about things like internal combustion engines and turbine, like you know, gas power plants or jet engines. We won't really get into that here because I think it's just not something that that I'll test you on now, but you'll be tested on it in the final. So here's a quick example. If we have an isentropic compressor, so this is like, remember, a compressor is like a pump, right? Its job is to increase the pressure. So we see at the inlet, we start at 300 degrees Kelvin, right? Close to room temperature. And we start at close to atmospheric pressure, 100 kilopascals. Now we increase the pressure by a factor of 8, right? Because we go up to 8 kilopascals. That's the job of a compressor, is to increase the pressure, right? And we're asked to find the compressor power divided by the mass flow rate, right? Sometimes I think they maybe call this the specific power in the textbook, but that's just compressor power divided by mass flow rate. right? And we're also told that this is an isentropic compressor. So you could get a problem like this where it's worded like, find the maximum possible power from the, or I guess it would be the minimum possible power consumed by this compressor, right? So that would be the isentropic state, right? Because there's no irreversibilities here. So hopefully we're familiar with the first law analysis, but here we'll assume that it's steady state, right? So that dE by dt term goes away, that the Q dot term goes away because it's adiabatic, the summation signs go away, and we'll get rid of the kinetic and potential energy terms, right? So we'll get this expression that we're used to when we're solving the first law for power. The W dot is equal to M dot times H in minus H out. Now, here we know then, so we do this, right? This is our first law. We made our assumptions. We demonstrated our understanding. We got this symbolic solution. But we know that the working fluid is air. So I can replace, if I assume constant specific heat, that delta H is equal to Cp times delta T, right? Anytime I write down an expression where I'm using Cp, Cv, or K, I also say, oh, I'm going to be using a constant specific heat assumption, right? So I sub this in, right? Now the problem wants W dot over M dot, right? So I don't need to know the mass flow rate. So this is going to be the power divided by the mass flow rate is equal to Cp times delta T. So this is great. I got a symbolic solution. The problem is I don't know the thing that I'm looking for, right? Cp, let's say that I look this up, right? But I know T in, but I don't know T out. So normally I'd look for a second independent intensive property at the outlet, right? Or actually, because it's air, if I just knew the outlet temperature, I'd be fine, right? But I don't know the outlet temperature. So I need to know something about the process, right? Maybe that's going to help me fix the state. And in this case, the thing that I know about the process is that it's isentropic, or that delta S across this compressor is equal to 0. We're assuming this is an ideal compressor, right? So we're going to say that I can use this expression because I've assumed that this is an isentropic compressor. So now I say that T2 over T1 is equal to P2 over P1, all to the exponent K minus 1 over K. All right, so now this is nice because I can multiply both sides by T1, but even though I don't know the temperature at the outlet of the compressor, I do know the pressure. Right, so now if I look up K in the textbook, right, or maybe it's given to me in a problem, then I know everything here, so I can find T2. Right, so now I know everything here, right? I can put some numbers into my calculator. The nice thing here is because in the brackets here, I've got a ratio of pressures. Right, so I don't really have to worry too much about the units as long as the units are the same, right? That's what I like about these, if you get pressure over pressure or temperature over temperature, just get them into the same units, and then you're just going to have a ratio here, right? So it's 8 times more pressure, right? Right, and then now I get an value for my exit temperature, or at least what the exit temperature would be if this was an ideal system. And then I put that into my original equation for power over mass flow rate. And now I know everything, at least for this problem, and I can get an answer, right? I'll check my units and I'll see that I get a power that's negative, right? And that's what I expect because a compressor is like a pump. I'm putting power in and work in is negative, right? So that's why I like to keep, and I've said this before, I always like to calculate power as hi-ho, right? Because that will always give me the right sign, and then I can use my, I can just add the works together, right? So that's how I deal with something that's like an isentropic compressor. Does anybody have any questions about this? So essentially, you're just looking to see, once you get to the point, oh, what's the fluid? The working fluid is air. And then you say, oh, it's an isentropic process, and that opens the door to using those isentropic expressions. right? So like we said that the power is negative there, which is what we expect, right? So now we're going to introduce the idea of what we call vapor power systems or the Rankine cycle, right? So the good news is we already know a little bit about the Rankine cycle. We did this when we were talking about ideal engines, right? Kind of the simplest version of a steam-driven power plant, something like a coal power plant, would be this schematic here, where we have 4 components, right? We have a boiler, which is where we're adding heat, right? That's where we boil the fluid, right? Aptly named. Then we have this turbine, right? And that's where the gas expands to produce power, right? But going into the turbine, we need high temperature, high pressure steam, right? That runs through the turbine. And then the whole rest of this stuff is just to get back to that high temperature, high pressure steam. So first we take that steam and we condense it, because liquid water doesn't cost us very much power to increase the pressure, right? So then we run this through the pump, right? But now we have high pressure liquid, we want high pressure steam, so then we boil it again, right? And we just keep going around and around and around, right? So this is the Rankine steam generation cycle, right? Now, hopefully, in all your classes, you kind of think this, right? Sometimes maybe ruefully, right? I remember when I was learning the heat equation, it was taught by a math professor, and it's like a differential equation. And he's like, oh, you know, this is like a heat equation, right? You mechanical engineers, and it's like we hadn't taken heat yet. So I was like, why do I care about this equation, right? And then the next year when I took heat transfer, I was like, oh, you know, that's why, right? So it's, you know, you can never get the timing quite right, right? But we care about Rankine cycles because they're super useful for generating power, right? You know, you know, if you like, I'm in a room with lights on, right? I'm talking to you through a computer, right? This is all power that's been generated and put out onto the grid, right? So in the US, right, I think these numbers are for 2019, right? So we're always trying to maybe move away from something like Rankine cycles, right? Because we'll talk about the downsides. But coal power plants and nuclear power plants both run on Rankine cycles, right? And in the US, that still accounts for just under half of the power that we generate and consume here, right? So this is a pretty big deal, right? It's kind of important in our lives, right? Even though, you know, this is kind of the beauty of the modern society we have, where everyone's kind of work or production is very specialized, but we have the ability to consume a wide variety of things, right? And part of that is because, you know, there's tons of people working on tons of different problems in the background that we never even really think about, but are kind of essential for the life that we live, right? So things like power generation, you know, when I turn on the light switch, I'm never really worried that it's not going to go on, or at least I'm rarely worried. I mean, I think the power here in Rochester goes out a little too frequently, but even still, it's like, you know, a total of 10 hours it's down a year or something like that, right? Which is kind of a remarkable achievement because, you know, people like engineers and technicians and you know, laborers, people are working really hard to make sure that we have things like power all the time, right? So when we look at this table, which is presented to us in the table, or in the textbook, sorry, coal-fired power plants, right? They run on Rankine cycles. Nuclear power plants run on Rankine cycles. And then, you know, there's some renewable type energy systems that are also trying to use Rankine cycles to generate power. I think this tends to be a fairly small slice of our energy pie, right? But we're always trying to drive that kind of stuff up so that we can limit the downsides of coal and nuclear power generation, right? Like I said, about 45% of the energy that we use here in the US is produced using Rankine cycles. So how does a Rankine cycle work, right? Like we said, it's a bunch of different components that we can think of as open systems that are stacked together, right? So now we're finally at the point where we understand how to do the Lego blocks, right? And now we're putting the Lego blocks together to make something cool, right? So in the Rankine cycle, usually you have something like water, right? Often it actually is water that's running through the Rankine cycle here that we talked about, right? Boiling, going through the turbine, condensing, pumping up to pressure, and just around and around and around, right? So usually it is water, but for some other like renewable sources, or particularly when your heat input is not that high, then you could use other fluids that boil with less heat added, right? So there's different kind of subsystems that are involved in Rankine cycles, right? So, the first thing that you need is you got to add heat, right? Because, that's what thermodynamics is. We put in heat, right? And we get work. Literally, that's what thermodynamics means, right? So the first kind of subsystem of this power plant is how do we get the heat, right? And this is actually usually how we classify different power generation systems, right? So we talk about a coal power plant where we burn coal, right? We talk about a nuclear power plant where we run a nuclear reaction to generate heat. We talk about natural gas power plants. It's kind of a big deal in the US, right? We're burning natural gas to get heat, right? So this is how we get heat, right? That's the first part. Then there's the part that we're sort of more interested in this class, particularly for mechanical engineers. That's what are we going to do with the heat, right? How do we take that heat in and turn it into mechanical power? The next part of the subsystem, or the next subsystem is, this is the reason, I don't know if you've ever seen old sawmills, right? Old sawmills have this big sort of paddle wheel that's often, in some kind of river, and the river is running. And as the river is running, it's turning that power wheel, or the power wheel, right? So that's going to be connected to some system, right? And then it's going to be connected maybe to some 4-bar linkage that's running a saw blade back and forth or something, right? It's great because then, engineers, we're not lazy, we're efficient, right? And it's not super efficient if you're the person sawing down the tree or cutting down the trees all the time, right? So we were sort of generating power, but you could only do that locally, right? The sawmill had to be beside the river for that system to work, right? So then what happened is we made friends with electrical engineers, or electrical engineers sort of started doing stuff, right? And then what we realized is I can generate mechanical power somewhere far away from my house, right? This turbine has a shaft that's spinning, right? Now I can connect this electrical generator to this spinning shaft. And what the electrical generator does is it takes in that mechanical power and puts out electrical power onto the grid. Now, when we start talking about AC signals, then we can sort of transmit that power over power lines for pretty far distances, right? So you don't have to be, in that sawmill right next to the river in order to get the power. You can put your sawmill wherever you want and just, plug your electric saw into the wall, right? The other part of this system, right? So remember Kelvin and Planck, they told us, yeah, you can run a heat engine, and that's what this is, what a nuclear power plant or coal power plant is, right? It's a heat engine because we're putting heat in and we're getting work out. But Kelvin and Planck told us we have to cool that system down, right? So the way that we cool this system down, at least in this figure, is we take that sort of low quality steam that comes out of the turbine and we cool it down, right? So here there's one of these big condensing towers. So you might see this, in The Simpsons, if people still watch that, right? And what happens is you spray this kind of low quality steam in here, right? And then what happens is the vapor goes up, but as it moves up this cooling tower, it starts to condense and falls down, right? So you get this cooled water down here, which you pump in back into the condenser. And then here, this liquid water gets heat from here, and maybe it boils and comes back in. So this is one way of doing it, right? But we could swap this out. Like I said, I did a little bit of consulting for a company that was themselves consulting for Ontario Power Generation when I lived in outside of Toronto. And the way they cool the nuclear plants there is they take liquid water out of Lake Ontario, right? And then put it back in. But there's regulations about how much you can heat that water up so you're not sort of destroying the ecosystem in the lake, right? So that's another way. So that's using basically Lake Ontario as a big heat sink, right? So we need a heat sink in our system. Right now, when we talk about Rankine cycles, we'll sort of be independent of these other parts, right? We're really only interested in what's going on here in subsystem B. We don't really care how we're generating heat, right? We don't really, in this class, talk about, how are we gonna, design an electrical generator to get that power onto the grid. And we're also not always super concerned about where the heat sink is, right? Whether it's a cooling tower like this, or it's, pulling water out of Lake Ontario or something, right? Really, we're worried about the guts. What's going on in here, right? This is what we'll be talking about, right? Our turbine, our condenser, our pump, and our boiler, right? That's what we're going to be looking at, right? And what's going to happen is in here, you have some working fluid, usually water, that's kind of just running through this system on a cycle, right? Just around and around and around and around, right? And generating power for us, right? So if you have a coal-fired power plant, right, then what we're doing is we're taking the chemical energy that's stored in these fossil fuels like coal, right? And we're liberating that into heat by burning the coal, right? Now, like all energy generation, this obviously has a downside, right? It's good because it puts power on the grid, and we like power, right? But it's bad because, there's emissions, right? So we don't like the CO2 emissions, right? So it lets us generate steam, which expands through the turbine, right? Because we're burning the coal, right? And then that ultimately, inside our Rankine cycle, we're using that to get mechanical power in this spinning shaft, and we turn that mechanical power into electrical power through this electrical generator. Right. So the cost here is that we're adding heat, right? And to add heat, in this case, we're burning coal. Now, I remember being a little bit disappointed when I figured this out, right? Or when I was told this, but really, a nuclear power plant isn't much different than a coal power plant. Somebody's figured out how to split the atom, right? Amazing, like one of the pinnacles of like human ingenuity, right? And a mechanical engineer looked at that and said, it generates a lot of heat. I bet I could use that heat to boil water, right? So it's like, really what we're doing is we just found a different way to boil water, right? So this nuclear reaction puts out amazing amounts of heat, and we use that to boil water, and that water just keeps running around in our system over here. So it's the same thing, right? It's not much different than a coal engine, right? Like that, an old style steam engine. We just figured out a better way to boil water, right? Now, as you probably know, one of the big benefits of nuclear is that there are no emissions, right? The downside, of course, is catastrophic failure can be very catastrophic, right? There's no form of energy generation that doesn't come with a downside, right? Right. So, it's our job as engineers, if you're involved in a project like this, to make these things as safe as possible, because the downside risk, while the chance of something bad happening is very low, the cost of something bad happening is very high, right? Not just the monetary cost, right? But the human cost too. Not just the human cost even, right? Like just the environmental cost as well, right? You can run Rankine cycles with solar energy, although this is typically you'd use photovoltaic cells if you wanted to do this, right? And you could do it a little more directly. But you could, if you had a working fluid in here, you could, have solar collectors that are heating up a working fluid, potentially boiling something like a refrigerant, right? And then you get vapor, right? And then you sort of run this heat around here, right? And then you're boiling your fluid in here and running it through a turbine, right? So this is probably not the only way, certainly not the only way to get solar power, and not the normal way we think of solar power generation, right? But it's certainly something that you could do. You could do this with geothermal plants as well. So geothermal means that we're taking heat that's being sort of developed in the earth, right? And we take that heat out in a system, right? And then again, we're using that heat to boil some working fluid to run through the cycle, right? So all of these different things, there's different ways to generate heat, right? But we're sort of heat agnostic when we're talking about Rankine cycles. That means we don't care where the heat comes from in this class. We just use it as an input into the system, and we'll analyze the guts of the cycle here, right? So the turbine, the condenser, the pump, and the boiler, right? It's the middle that we care about, right? We don't care how you're generating heat. We don't care how you're rejecting heat either. We're going to analyze the middle of the system, because this is where the efficiency gains can happen if we're trying to develop a system like this. So a Rankine cycle, at least the most basic form of Rankine cycle, would look like this. In practice, they're much more complicated, and we'll get into some of those complexities because, we fight tooth and nail for any sort of percent increase in efficiency that we can get. But it makes sense to start at the beginning, right? And the beginning, the most basic version of a Rankine cycle we can have has one turbine, one condenser, one pump, and one boiler. And what we're going to do is, I guess here it says, it doesn't matter where the heat comes from. The way we're going to analyze the system is we're going to look at these components, and we don't care where the heat comes from, right? And we talked about we can analyze a system like this globally by talking about its thermal efficiency. So now we take the energy benefit, that's going to be the net power produced. So the turbine power, which is positive, plus the pump power, which is negative, right? That's our net power. That's the energy benefit. And the cost is that we had to add heat, either by burning coal or maybe by running a nuclear reaction, right? So our thermal efficiency here is the net heat divided by the heat in. But we don't care where the heat came in when we're calculating the efficiency here, right? That's just a characteristic of the cycle. So like I said, this is the simplest case, and it's got 4 components. It's got a boiler, a turbine, a condenser, and a pump. Right, so what we do is we can take an open system analysis on each of these components and then look at them together to see what's the net work and what's the heat transfer in, right? And then we can find the thermal efficiency. Right, so if I was drawing a TS diagram, and remember we did this already, I sort of sneakily introduced you to this topic already, right? So our boiler, in this case that we talked about before, went from saturated liquid to saturated vapor. And then our turbine was producing power. This was an ideal or isentropic turbine when we talked about it. So we went vertically down from state 1 to state 2s, and we produced power in this turbine. Then we went through the condenser. We went from whatever quality we came out of the turbine here down to some lower quality. Usually you'd come right down to here, but remember for this example, I wanted to be all under the vapor dome. So we came down to here, right? And then we added some power in the pump to get back up to the pressure that we wanted, right? And then again, you'd go through the boiler to get back to this high temperature, high pressure steam that you want to go into the turbine so that you can generate power. And this, it's called a cycle because we just keep going around and around and around. Right? So how do we analyze these things? Right? So first, we like to draw the TS diagram. This is probably what a real system is going to look like, a little bit more than that last one that we looked at, right? Because we're going to condense all the way here to a saturated liquid, right? So we're going to have some subcooled liquid that goes into the boiler. The textbook starts the examples starting here at saturated vapor, just when we boiled the whole thing. But you can go to superheated vapor over here as well, right? So this is what a TS diagram looks like. You'll be expected to know how to draw these things, and you could certainly expect to see that on an exam, right? Even this second exam, not just the final. I like to draw the main energy component of each of these processes on the diagram, but you don't have to do this. But I like to remind myself, this is where we're adding heat. So my heat line, which is wiggly, goes into the boiler. This is where we're producing power, right? Work out. So my arrow goes out of the cycle. Here's where we're rejecting heat. Here's where we're adding power in. I like to draw those on, but you certainly don't need to. So if we want to know the thermal efficiency, we want the net power divided by the heat transfer rate in. So the net power means I got to look at the turbine power and the pump power, right? So how do I find those, right? The textbook will tell you, right, that it's the turbine power minus the pump power. What the textbook doesn't tell you is that it's taking absolute values of those expressions. Instead, I like to use the first law and add those things together, right? The other thing that we'll need to do here is look at how much heat is coming in to the boiler. Right? If I know those 3 things, then I can go and find a thermal efficiency. Right? So I can talk about my Rankine efficiency, at least for this system, as the magnitude of the turbine power minus the magnitude of the pump power divided by the heat added at the boiler. Right? Or if I want to drop all those absolute value signs, the way that I like to do this, because I always like to get these expressions, W dot and Q dot, from the first law, so I don't mess up the sign, right? I let the first law take care of the sign for me. But when I do that, I got to remember that I'm adding the turbine power to the pump power, right? And that gives me the net power. So for common assumptions, if I'm talking about, so for all of the components, I'll say they're at steady state, that there's one inlet and one outlet, that there's no kinetic energy change, no potential energy change. And then I got to pick, is the component adiabatic, right? So usually the turbines and pumps will assume are adiabatic, that there's no heat loss from those components, or are they passive? So if I'm looking at the boiler, when I'm trying to find the heat transfer rate, I'll often assume that that's passive, right? That there's no pressure losses or things in the system, no fan blades in the system either. So I cancel out that W dot term. The other thing that I do when I have to talk about cycles, I'll assume that there's no friction losses in the tubes that connect the different components, and that there's no heat losses in those tubes either. Now, this isn't really true, but it makes your life a lot easier. I think at one point there's a question in the homework where you don't make those assumptions, and that means that you have to do first law analyses on the individual pipes that are connecting our different components. And while that's, that'll get you a more accurate answer, in terms of this class, it doesn't really allow you to demonstrate your understanding of thermodynamics any better. So we typically make those assumptions so we're not fixing an extra 7 or 8 states, right? So for each component that's adiabatic, right? So this is going to be the turbine and the pump. We'll get that power is equal to H in, or M dot times H in minus H out, right? We remember that the dwarves are telling us, right, they're working hard, right? And they're singing hi-ho. So if I'm trying to find power, which is like work over time, then I get M dot times H in minus H out. If the system is passive and I'm trying to find the heat transfer rate, then it's M dot times H out minus H in. It's a good thing to kind of remember what these things look like. But again, on your exams, I'm always going to encourage you to take the extra 20 seconds and write down the base level of the equation, make your assumptions and cross terms out, because that's how you demonstrate your understanding. If you can make all the assumptions we expect to make, these are going to be the answers that you'll get. The turbine power. So on Rankine cycles, we typically label state 1 as going into the turbine and then go around the horn from there, right? But I could label a different state 1, and then if you only memorize these equations, you'd get totally wrong answers if you didn't understand what you were doing, right? But typically, if state 1 is the inlet to the turbine and we just go sequentially around the cycle, then you get M dot times H1 minus H2. That's the turbine power. We expect that to be a positive number. The heat rate out at the condenser is M dot times H3 minus H2. We expect that to be negative because that's heat out. The pump where we're putting power in, right? Again, that's M dot, now it's H3 minus H4, in minus out. We expect that to be negative because we're putting power in. The boiler where we're adding heat, we expect that to be positive, and it's M dot times H1 minus H4. I've left subscripts on the mass flow rates here, but if you do a conservation of mass analysis like we did previously in the example, and we'll do again in the example tomorrow, you'll notice that all these mass flow rates end up being the same. Right, so then after you did this symbolic solution, then you say, oh, what's the fluid? Oh, the fluid's water. Okay, how do I go through and fix all these states and find numerical values for these powers and heat transfer rates? So now that I have expressions for the individual components and the power and the heat transfer rate associated with those components, I can find a thermal efficiency, right? So I put the equations on the last sheet into here, right? I notice that all the mass flow rates are the same, right? Because we're steady state in one inlet and one outlet, and all these things are connected in series. So the mass flow rates drop out, and my thermal efficiency is just an expression of specific enthalpies, right? So I can look at this like this, or I can use little w dots. That's like big W dot over M dot, right? Or sometimes I think the textbook calls it specific power, or specific heat rate. That's big Q dot over M dot. right? So I could write it down like that. This is helpful because sometimes you don't know the mass flow rate, but you can still find the thermal efficiency if you want it. Or it's just one less number to keep punching into your calculator. And if you're like me, I'm really good at making mistakes when I put numbers into my calculator. So, anything that I can cancel out, that helps me avoid making a mistake. Right? So this is the expression that we did last time, right? So we'll go through a full example next class, so don't worry. But we had this ideal efficiency or ideal Rankine cycle, although we didn't know it was called a Rankine cycle before. We found all these H's. When we put the value into our thermal efficiency, we got that the thermal efficiency in this case was just over 55%. Right? Now, if you think about, like, in terms of academic performance, you might look at 55% and say, man, that's not very good. But in terms of a heat engine, that's actually reasonably high. That's not an unreasonable thermal efficiency for a power plant. So you might look at it and say, why, right? So remember, Kelvin and Planck, they told us that in order to run a cycle, for a long period of time, you have to take the heat in, but you also have to reject heat as well. Now, the downside of using water in Rankine cycles is that you have to lose a lot of heat to go from steam down to a liquid, right? Remember, Watt's pot never boils, right? That means it takes a lot of heat to boil water. It's also true you have to reject a lot of heat to condense water. So remember that the net work is going to be the heat rate in minus the heat rate out. So because we have to reject a lot of heat when we're condensing liquids, it means that that's less heat available to or less power, less energy available for us to turn into power, right? So condensing liquid is something that can rob us of efficiency, right? So that's kind of the downside of these Rankine cycles, is that the thermal efficiencies, although we're always working to make the efficiencies higher, there's kind of a natural limitation here because we have to condense the liquid, right? One of the things we then try to do is maybe scavenge some of this heat, right? So this heat output from this cycle maybe could be a heat input into some other cycle. But one of the reasons that this was kind of one of the first kinds of power plants that we looked at is because the backwork ratio is relatively low, right? So what's the backwork ratio? So this is looking at the ratio of the power consumed by the pump to the power produced by the turbine. Because the power plant is the first consumer of the power plant, we would like this backwork ratio to be relatively low, because that means at least the majority of the turbine, of the power that I'm producing in the turbine, is going out onto the grid. It's not being consumed by the pump. If you had a backwork ratio of 1, right, 100%, then there'd really be no point in running your power plant, because you would just be running your power plant to run the pump so that you could run the power plant, right? So you wouldn't be producing any power. You'd just have kind of the system that was running for no reason, right? The thing that so again, if everything is one inlet and one outlet and at steady state and adiabatic, right, then we get just a ratio of delta H's, right? So delta H across the pump divided by delta H across the turbine, and backwork ratios we'd normally report as a positive number, even though the sign of the pump power is negative. The nice thing about these Rankine cycles is that the backwork ratio is very low, which is what we want. So this means that, it was less than 0.5% in this example. So that means like 99.5% of the mechanical power we're producing at the turbine goes out onto the grid. So that's the nice thing about Rankine cycles, is they have low backwork ratios, right? But the thermal efficiencies, we'll see one of the big reasons that the U.S., has moved so heavily to natural gas power plants in the recent past is that they tend to have higher thermal efficiencies. They're also, we also have an abundance of natural gas, and they're less expensive to build than like a nuclear power plant, and they take less time to build too. So, there's more than one reason, but one of the reasons is that backwork ratios are fairly low. So I realize I went over a little bit, but that is all that I wanted to talk about today. Next class, we'll go through an example on how to do a full analysis on a real Rankine cycle. I'll stick around if anybody has questions.
All right, thank you, Professor.
Yeah, no problem. Have a good one.
Thank you, Professor.
You're welcome.